Today, what would we see if we approached the speed of light? Let's embark together on a spaceship that accelerates away from Earth, moving faster and faster. What would we see when continuously accelerating? What optical effects would occur? And if we tried to exceed light speed by bending space-time like in sci-fi movies, what would we see? Answering these questions will lead us to explore many fascinating phenomena of our universe and immerse ourselves in the heart of special and general relativity. Our spacecraft is initially at rest at takeoff. Once launched, we begin to accelerate. We imagine that its propulsion system allows us to accelerate constantly for as long as we wish. As we gain speed, we move away from Earth by accelerating more and more. One would think that the speed would eventually become unbearable. However, this is not the case. Speed has no effect on our body. When two trains cross, it is impossible to feel whether it is our train or the other that is at rest. Similarly, inside the spaceship, we cannot feel its speed but only its acceleration, the thrust of the reactors, which presses us against our seats. If this thrust is reasonable, it will be perfectly bearable throughout our journey, even when approaching the speed of light. There is, nonetheless, a risk associated with very high speeds, a collision at high velocity. A mere speck of dust would cause colossal damage if it hit us. Fortunately, our ship is equipped with a force field that repels dangerous objects and allows us to roam freely through space. As we accelerate, a first optical effect appears, an aberration of light. The stars in front of us, which we are approaching, seem to gradually move away. The sky contracts before us. To understand this, think of a common situation. You are in a car driving at high speed, and it starts to rain. The rain falls vertically from top to bottom, but as the car moves forward, you receive raindrops on the windshield from the front. The rain does not appear to fall from above, but from the front, as if its trajectory were tilted. The more you accelerate, the more the rain seems to come from the front. In our spaceship, the optical effect is perfectly analogous. The star's light comes from a certain direction, but as we accelerate, the light rays appear to come more and more from the front. Their direction seems different when we are in motion. This is the aberration of light. As light focuses in front of us, its intensity increases, while behind us, the sky seems to widen and become darker. The aberration of light results in another strange phenomenon. Let's imagine we are moving through an immense grid representing the fabric of space. Ordinarily, we would see a straight grid made up of straight lines converging in front of us due to perspective. However, as we speed up, the aberration phenomenon distorts the image of the sky around us. As the days go by, the grid seems to contract forward, and the straight lines bend. If we were to go past an object, it would appear slightly angled in our direction. This is called the Tell-Penrose rotation. As we move very quickly, images of objects seem contracted in front of us, and perspective is strongly distorted. We often hear that the farther we look into space, the further we look into the past. Indeed, the light we receive from a distant star must travel billions of kilometers. This journey is not instantaneous. It takes time for light to reach us. As a result, we see the star as it was in the past when it emitted this light, perhaps several thousand years ago. Who knows how it might have changed since then? Looking out from our spaceship, the same phenomenon is at work. As we move away from Earth, the planet's light takes longer and longer to reach us. If we could zoom in with a telescope, we would see people on Earth evolving in slow motion. This is the Doppler effect. Each tick of the clocks on Earth takes longer and longer to reach us. We receive light rays in slow motion, and their intensity seems to weaken as the image of the planet shifts towards a red color. In front of us, the opposite effect occurs. The ship catches up with the light, and the stars seem to get brighter. They shift toward blue, and their clocks appear to tick faster. With precise enough equipment, we could measure the aberration and Doppler effects since the start of our acceleration in space. However, if we decided to end our journey and return to Earth, these effects would have had no impact. They are only optical illusions due to the way we receive light while moving. After several hundred days, however, as the reactors push us ever faster, the ship begins to approach the speed of light. At such speeds, some phenomena will no longer be mere optical illusions, real physical effects will kick in with irreversible consequences. Special relativity comes into play. A first consequence of relativity is known as time dilation. Our universe is a huge four-dimensional fabric called space-time, made up of 3 dimensions of space and 1 dimension of time. Inside space-time, all bodies trace a trajectory since they all advance toward their future. Before takeoff, our ship was moving in the same way as Earth, towards the future. But by picking up speed and zooming away from Earth faster and faster, our trajectory gradually deviates from that of the planet. The axis we call time is no longer aligned with the time axis of people on Earth. If we decided to turn around and come back, our clocks would have measured a different time, and we would have aged less than Earthlings because our trajectories in space-time would have been different. Another key consequence of special relativity is called length contraction. When a body moves close to the speed of light, its length gets contracted in the direction of its motion. From the spaceship's perspective, the entire universe is moving backward. For us, the universe is contracted along our direction of motion. As such, the length of the journey to reach our destination is shorter than expected. We are not talking about optical effects anymore, but about a physical and concrete phenomenon. If we tried to reach a distant star, the journey would genuinely seem shorter to us, it would take less and less time the faster we moved. Contrary to popular misconception, it is possible to travel thousands of light-years in just a few seconds. If we moved almost at light speed, the journey would even seem instantaneous to us. For people on Earth, however, several thousand years would have passed. By accelerating more and more, we might expect to eventually reach the speed of light. What would we see then? The answer is that we will never reach the speed of light. Even if the ship accelerates constantly, the speed of light is absolute. You may try to catch a light ray, but from your point of view, it will always escape at the same speed, the speed of light. At best, our ship will continue to accelerate forever, and our field of vision will continue to shrink until forming an infinitely bright spot in front of us, surrounded by a completely black sky. Almost at light speed, all optical effects would become extreme. As we catch up with light rays before us, they all seem to come from the front, while the rays behind us can never reach us. To conclude, nothing can ever move faster than light through space. But there might be a way to circumvent this rule. Nothing prohibits space itself from moving faster than light. The theory of general relativity teaches us that the fabric of spacetime is dynamic, it can bend in multiple ways. We could imagine creating a bubble around our spaceship that propels faster than light. This is called a warp drive, in reference to science fiction. Our ship would remain motionless, surfing on a wave of faster-than-light space-time. However, producing a warp drive would require bending space-time with huge amounts of negative mass, a form of matter that does not seem to exist in our universe. That said, mathematics still allow us to model what we would see in such a situation. If we looked from outside, the warp drive would seem to appear out of nowhere. Looking from the inside, we would see the sky contracted in front of us and very bright behind us. The universe would look extremely dark, and a whole patch of the sky would simply vanish from our view. A cone of the universe would remain permanently invisible.